In this video, we're going to be looking at center of mass. Specifically, we're going to define what center of mass means and then use the concept of center of mass and calculate where it is for various methods. So first off, definition. This is the location of the mass-weighted center of an object or a system, which is kind of a weird definition. You know what a weighted sum or average is, and that's kind of what we're dealing with here. So if you imagine this shape, that dot represents the center of mass right there. It's not halfway up because more of the mass is down at the bottom than there is at the top. Similarly, if you were to take two discrete objects, right, like this small and large mass, the center of mass between them would be closer to the more massive side. Something like that. That would actually also be the balance point if those were attached by a rigid rod. So center of mass lets us do a lot of things. It helps us understand balance, that last example, and stability, basically what needs to be supported for something to stay upright. It also allows us to figure out what point things will rotate around and a few other things like complicated motions with objects that are not simple. But it's key for analyzing various systems with multiple pieces. So when it comes to balance and stability, I don't know if you've ever seen one of these toys, this little balancing bird. It actually has weights out in the wings so that even though it looks like it's balancing kind of out in front of itself, it's perfectly balanced. Similarly, if you take something like a broom, a hammer, anything where there's more mass on one end, you sort of try to balance it on your finger, you'll see that there's a point, usually close to the, certainly close to the massive end, where it will balance. You have a center of mass. I have a center of mass. We all do. If you stand on one leg and you try to do it without shifting your body left or right, or if you try to stand up just by crossing your arms and standing straight up without even leaning forward, you'll notice that you can't actually do it because your center of mass is not supported. And you will tip over if your center of mass is not supported. So when it comes to complicated motions, if you think of something like doing a dive and a flip off of a board, hopefully not into shark-infested waters, right? You can follow the center of mass and it will behave just like all of the simple physics says it will, even if the more complicated motion is harder to track, right? The center of mass will follow the parabolic free fall projectile motion trajectory, even though if you track, say, your head or your feet or your hand, it would be a much more complicated motion, right? Simplified there. So we can take a quick look at this video, and you can go watch it again. But this is tracking one end of a tennis racket, which is, of course, a complicated object where the center of mass is not exactly obvious on first attempt, right? But if you do that, and then you go ahead and you follow, say, the handle, and we kind of draw a track where the handle goes, the handle's motion is fairly complex, right? That's definitely, it's kind of a cycloid shape, which again is not as easy to model. But if you just watch the center of mass, and this teacher found the center of mass beforehand, and you just follow it, right? Now suddenly the motion is very, very simple, which is kind of a nice thing to look at. This also can simplify some really complex problems. We did this problem back at the end of the last unit using integration to figure out how much work it took to lift this chain up, talking about each little piece. Some of you may have already seen that, well, it's sort of the same as if you can just find the center of mass of that segment, right, and think of lifting that up to the top, because the top only moves a little and the bottom moves a lot, and if it's an even mass distribution, you can find the same result. This also works for things like, star systems, binary star systems, where two things are cycling around what seems like nothing, but what they're actually circling around is the center of mass of the system. And so this leads us to a really interesting thing that's related to the conservation of momentum. If the external force on a system is zero, then the motion, right, the system itself will not accelerate. And this means that the momentum is conserved, linear momentum, but it also means that the center of mass stays in one place or is moving at a constant velocity. More on that later. This is another really interesting one. If you take two sort of carts, these are air tracks, so they're floating on air and they can be pushed. And they have a spring between them that'll pull them together or push them apart. And it's hard to see in this picture, but you'll see in the video, there's a tiny little bead in the middle that represents the center between the two carts, so the center of mass of the whole system. And so if you initially let them be pushed from the wall, they will accelerate. But then if the net external force is 0, they should move at a constant velocity, even though the motion itself will be relatively complex. So here, I'm going to move myself out of the way so you don't have to see me, and we can watch this video. So first, that's actually kind of annoying. Okay, I'm going to pause the recording here and we'll come back to it. Do a little edit. Okay, so here's that video from the MIT lab that we'll watch. I'll kind of narrate what's going on. They're calling this the push me, pull you, because one of them will push and one of them will pull. Under bright white lights, if you watch it, there's the air track, there's the two carts, there's the spring in between them. They can push them apart, pull them back together, so they can't actually escape each other. So we're going to start just by turning on the air and letting them move. So initially they accelerate, but then one starts, one stops, go back and forth. Speed up, slow down, speed up, slow down. You can get a close-up here. You can watch sort of that bead in the center. And if you look closely, you can see some sort of interesting results there. More on that in a moment. You'll see as it gets to the end, then of course it gets hit by an external force again and changes direction and so on. The next part of this, they're going to turn off the lights, and the bead in the middle, that center of mass, will glow. It's that little dot under black light. And so when they turn on the air track to watch it go, if we just can watch the center of mass, you will notice that the center of mass is moving at a constant velocity, even though the two different sides and parts of that are actually speeding up and slowing down, speeding up and slowing down. And it moves at a constant velocity until the system receives an external force, which causes it to start moving the other direction, and again, move at a constant velocity. So that's push me, pull you. Which hopefully makes a little sense. Next up. Come on. There we go. So how do we actually find the center of mass? Well, there's 3 different methods we can use. Symmetry, when things are nice and symmetric and simple. Experimentally, by balancing things. And mathematically, which with a small system of particles, that's pretty straightforward. We'll look in a later video on what happens if it's a continuous distribution of mass. So if you have something like a sphere of uniform density, it's pretty obvious that the center of mass is right at the center of the sphere. And if you have anything like a cylinder or a stick or a roll of tape, right, anything where it's pretty obvious where the center of it is and it's sort of got uniformly distributed matter, you could be pretty confident the center of mass is there. If you have something strangely shaped like this, maybe it's a barn, I don't know. One thing you can do is you can actually just hang it from various points and draw a line straight down, and where all those lines intersect, that would be the center of mass. Or you can repeatedly move it around on your finger until you find the point at which it balances. So we are going to look at a system of particles or composite bodies where we have discrete objects. We can figure out where the center of mass is and then kind of combine them. We'll look at rigid extended bodies with a uniform density next time. So for a system of particles, we need to pick an origin, we have a coordinate system, and then we identify where those objects are and what the mass of each of them is. And so the center of mass, sort of x coordinate here, is mass 1 times x1 plus mass 2 times x2, and so on, divided by the total mass. This is that weighted average for the position. So here we go. Where is the center of mass? Well, we could predict that it should be closer to the more massive object than to the less massive object. We can do the Actual calculation, 5 kilograms times 0 meters, 10 kilograms times 2 meters divided by 15 kilograms, 1.33 meters. Indeed, closer to the 10 kilogram than to the 5. If we check, right, what would happen if mass 1 goes to 0? Well, then the center of mass would be at 2 meters, right, just inside the 10 kilogram mass. And if mass 1 is 10 kilograms, where would it be? It would be right in the middle because there's an equal or balanced setup. Right? If you have more particles, you just add another term. So generally, it's 1 over the total mass equal times the sum of mi xi. In more than one dimension, you would do the y and the z coordinate if needed. So what about something that's a composite body? Well, here we have 3 blocks stacked on each other. So they're all individually uniform density. And so it's pretty easy to say, well, the center of mass of each of them is just in the middle. The 20 kilogram block has its center of mass at 2, 2, the 9 kilogram at 4, 5, XY pairs, and the 4 kilogram at 5, 7. So we can put all that together, 2, 4, and 5, divided by 33 kilograms to get 2.9 meters for the X, and then in the Y direction, similar 3.4 meters. So we would say, that the coordinate system, if you wanted to write it as an ordered pair, would be 2.9, comma 3.4, or you might say at X equals this and Y equals that. So there's other things you can do. Imagine a piece of wire that's bent into this sort of U shape, right? Well, if its total length is L and its total mass is M, each section, being L over 3 in length, would give you a third of the mass as well. So you can set up X and Y coordinate system. Right in the middle is an easy way to do it, right? Each piece has its own center of mass. If you add those up, it's certainly going to be along that Y-axis, right? By symmetry, in the X direction, the X coordinate is 0. And in the Y, we can plug in all the values, and you end up with L over 9. So to find this center of mass, we didn't even need SI units. Right? That's the nice thing about center of mass. If you're always using the same units for a problem, you don't actually care what units they are in. Here's another one that's kind of interesting, and this is how I'll finish up. If you have a uniform circular plate and then you cut a rectangle, or in this case, a square, out of it, where is the center of mass? Well, it might not be immediately obvious, but it's certainly probably reasonable to say it's somewhere over here, near where this X is. It's going to be moved away from the center of the circle because we've taken mass out in the upper right-hand quadrant. So what's a smart way to orient your coordinate system? Well, probably so that the center of mass of the object is along one axis, and that the cutout piece has its center along an axis as well. So the center of mass in the Y direction is 0. That simplifies everything for ourselves. And so we can kind of rotate the whole picture around if we want. So what can we do to find the X center of mass? Well, let's think about it this way. The whole circle is equal to the circle with the cutout plus the cutout, right? So we could kind of reverse that and say, well, where's the center of mass of the whole thing? Where's the center of mass of the cutout? And then actually subtract them from each other. And then we can find those pieces. We could do a little ratio here if we wanted to, and we find that the center of mass is at about negative 0.95 centimeters. All right, that's the basics on center of mass. The big idea here is that the center of mass is this special point. It's really the dot that we've been using in our free body diagrams. This is where an object will balance if it's supported. It's the place around which it will rotate if you just toss it in the air, and it is the weighted average of all the mass in the system. So there you go.